Hi everyone. So we'll be starting out pretty soon. Uh, yeah. So let's see. Okay, we already have some people joining us. Hi Martin. Okay, so we will start as soon as we have, like, let's just wait for a few more minutes so that people are joining. Okay. Okay, I think it looks better now. Okay, hi everyone. So welcome to this PyData event, the first one in a long time. Yes, as you rightly said, Pablo. Yes, it's been a long time, but we are finally happy to see or happy to start the meetup series again. So, without further delays, uh, yeah, I mean, let's see. So we have around 8 people in the chat. So if you can post in the chat where you're joining from, it would be really cool. Let's see where we have people from. Thanks, Dimitri. Okay, so to start with, let me just, okay. So we have people from Munich. So it's like a local community, even though we are currently doing this virtually, but still good to see you people and lots of people who we know from the in-person events. Really nice. Okay, yes. We have Barak, who's also joining us from Munich. Hi, Barak. Yeah. Hi, Omid. If I don't know if that is the real name, but yeah. Okay. So the basic idea of this meetup is that we go through like some introduction about what PyData is about and what we do in PyData Munich, and then we'll quickly go to the speaker for tonight, who is going to talk about autoencoders for computer vision. Okay. So for those of you who are not familiar with PyData, it's the educational department or educational program of NumFocus, which is a non-profit organization based in the US. And PyData mostly organizes conferences and meetups all over the world. And last year, there was a virtual conference in November, and the videos are already published online. I mean, there are some really cool talks from it. So you can actually look into it. It's on their YouTube channel. And so, what is NumFocus? So as I mentioned earlier, NumFocus is like a non-profit charity which funds a lot of open source projects in the data science and machine learning space area. Like, I'm pretty sure most of you would have used at least one of these libraries, like libraries or frameworks like Jupyter or NumPy, Pandas, Matplotlib, like scikit-learn, etc. And so basically, NumFocus funds all these projects and supports them both financially and like with resources. And okay, so I think this is not that relevant today because most of you are from Munich, but just in case you're joining from somewhere else, we are in the southern part of Germany. And yeah, this is like one of our most famous city centers. And we are also really famous for the Oktoberfest. Unfortunately, it was cancelled, as we all know, due to the pandemic, but hopefully it will be held again once the crisis is over. And so what are we doing at PyData Munich? So most of the times we organize like tutorial style talks. We try to do it every month, but we have been inactive for quite some time now. But we are starting to do these events more regularly. And most of the times you have uh, the speakers talking using Jupyter notebooks, telling about some concepts, showing some real code, and also sharing these presentations and notebooks afterwards so that you can like use them afterwards. And we are always looking for speakers. Uh, so please feel free to reach out to me or one of the other organizers, and we will help you out in creating the talk. Yes, and Dimitri wants to share that, yeah, he also shares a lot about these Python packages in his channel. So if you share the YouTube channel link later on in the meetup group, people can also follow you there. And so this is our first virtual event. So we are still quite early. So we still are basically trying out different technologies. And so if you have some feedback or suggestions for the next event, please let us know. And okay, so for today's event, the talk would be streamed on YouTube as where you are all watching this. And if you have some questions, feel free to post them on the chat and we'll get to them uh, through to the speaker. And after this event or after the main talk, we would have like a networking call. I mean, it's not necessarily related to the talk. You can talk about whatever you feel like. And Sijuade or our speaker for tonight would also be there. And feel free to share your feedback. Yes, how are we on time? Okay, so we still have a few minutes. So yeah, I think that's most of what I wanted to share in terms of the PyData group and community. So without further ado, I'll introduce our speaker for tonight. So our speaker for tonight is Sijuade Oguntayo. He's joining us from Nigeria. So he's like the lead data scientist and machine learning engineer at Omdena. And they basically work on a lot of uh, machine learning projects for nonprofits or yeah, like basically machine learning or data science for good. And yeah, let me just add him to the stream. Hi, Sij.
Hello. Hi,
How are
everyone.
you doing today?
I'm doing good. How are you?
Yeah, good. Thanks. Thanks for joining us
Nice.
all the way from Nigeria.
Yeah,
Like,
to be.
uh,
Good to
I
be
think
here.
I lost you. Yeah. Okay. Thanks. Yeah. This is one of the good things about
Oh,
the virtual events, right? So you can have speakers from anywhere. Okay. I think we have some network issue there.
hello.
Okay. Yes. So good to
Oh,
have you back.
yeah. Yeah. Sorry about that. And it's been
Yeah.
fine
And
so the moment you introduced me, you started misbehaving. Cool. Yeah,
Yes.
it's really good to be here. Let's talk about autoencoders.
Yes. So I think we have like a couple of minutes. So I mean, we can also talk about something that you are doing, or like, yeah. So
Yeah, sure. What
so
what would you like to know?
what's your current project, or what was the last project that you were working on?
Um, so yeah, with Umdena, last project I worked on, it was a computer vision problem.
Mhm.
So we the work was done with like a social impact company building laser weeding machinery for
Mhm.
so yeah, to detect weeds and then automatically laser them. So yeah, that was
Yeah.
fun.
Yeah.
Current project, there is no current project, but
Mhm.
I did enter into the are you familiar with the World Data League? It's like a data
Uh,
science competition.
okay. I'm
Yeah,
not,
yeah,
but it's good to know.
yeah.
World
It
Data League.
starts on the 1st of April, and
Okay.
I'm really excited about that.
Okay, cool. So basically, they give you a problem and you work on the problem, or how does it work?
Yeah. They give you a theme. So the theme
Mhm.
so far is at the moment the theme is data-driven sustainable cities.
Okay.
I think it's either data-driven cities or sustainable cities, one or
Mhm.
the other. So
Okay.
yeah, so it's like an 8-week challenge,
Mhm.
and so you come in with your team. So I'm part of a team of 4.
Mhm.
So every 2 weeks you do a round and then you move on to the next round.
Okay.
So yeah,
Sounds interesting.
we'll
Yeah, I should check this out.
we'll
Yeah.
see. Yeah, check it out. I will send you the link.
Yes. Okay. So I think we are quite close to your starting time. So I think I'll leave you to your presentation. So I'm pretty sure we are all eager to know about autoencoders from you. How does it work into practice?
Sure.
Yes. So I'll just go off the stream and then share your screen, if that is fine. Okay. Let me just remove my.
Cool. So we can start. This is a very short presentation. So after the presentation, we will move on. So 2 collab notebooks have been prepared just to give a sort of practical demonstration of autoencoders. So yeah, we can start. So autoencoders. So what are autoencoders? So an autoencoder is an architecture that lends to represent some inputs by compressing it into a latent state and then reconstructing the inputs from that representation in an unsupervised manner. So it's an unsupervised machine learning technique. Um, why exactly is it important? So the idea is by compressing an input into a compressed state, the model lends a meaningful representation of the data. So it's as meaningful a representation as possible while keeping the data while keeping the data as small as possible because it's compressed. Here we have a graphical image of autoencoders. So this would be the encoder part where an input is compressed into a latent space representation. And this second part would be the decoder, which reconstructs that same image. So now the first question you might ask is why exactly is that important for something to output the exact same or at least close to the exact same thing that came into it? And the point is right here in the middle, because here the model is able to learn something compressed, something small, through which it is then able to reconstruct the image. So by doing this, we now have a meaningful representation of the data. And these has many, many applications. We will get to some of them in a second. So yeah, so they are, so here are the components of an autoencoder. We have the encoder, which is the part that compresses the inputs into a latent space representation. We have the decoder, which is where the representation is reconstructed back to the original input image. We have the bottleneck, which is this latent space representation. And then we have so the reconstruction loss we use. This is how we measure how well the output of the decoder, or how close the output of the decoder is to the input. So one of the main uses of autoencoders is for dimensionality reduction. As we can see, by reducing the input image, which is this big, into something smaller, we now have something smaller to use for whatever our purposes. So now this is also useful outside of computer vision. It is used in audio, and it's also used in for cross-sectional data. So I actually have some experience. I worked on a time series problem last year, where the number of features was really large. So we had about 300 features, and autoencoders were used to compress the features into something smaller, which was then fed into a machine learning model. In this way, it was used exactly like principal component analysis, PCA. The only difference being that the encoders and the decoders can be nonlinear, whereas PCA is a linear operation. So there are many different types of autoencoders. The sparse autoencoder, denoising autoencoder, deep autoencoder. We will be going into some of them further down. So these are some common applications of autoencoders in computer vision. One of those is denoising. So with denoising, we can train a model to remove noise from an input image by corrupting the data ourselves, and then train the model to reproduce the original input. So one of the notebooks we shall be going through actually deals with this. Another common application is image transformation. And one example of this is where we feed a black and white image into a model, and it outputs a color image. And there is also image completion, where parts of an image is missing, and we reconstruct that. So we shall also be going through a notebook that shows this in practice as well. Finally, the last project I worked on, as I mentioned, with Umdena, was dealing with crop weed classification, and we made use of autoencoders as well. This particular image is from a research paper, which is linked here, where this is used as well. So you can follow the link to get more details. So we can move on to the practical demonstration. So first, we shall be exploring the denoising notebook. So the plan is to connect this live so we can all run it together. We'll be using the MNIST datasets for digits. So this is a dataset of handwritten digits from 1 to 9, I believe, from 0 to 9. Okay, so we are connected. We run this to load the datasets. This downloads the datasets. The datasets have a dimension of 28 by 28 pixels and one channel, because they are, well, I don't want to say grayscale, but it's a single channel anyway. So this is an example of an image in the dataset, number 5 here. We can split this into train and test. And here we normalize the data by dividing by 255. We also convert to float 32. So this is the network architecture. It's a very simple architecture. We only have two convolutional layers as the encoder. This represents this is the latent code representation, and this is the decoder, which is also two convolutional layers and two upsampling layers. For the loss, we are using the binary cross entropy loss and using an Adam optimizer. This is the summary of the model. Again, input of 28 by 28 pixels, output of 28 by 28 pixels. Now, so this is where autoencoders really shine. So now the difference between what was described before with a standard autoencoder is a standard autoencoder reconstructs the exact same input it gets. In the case of the denoising, what we are doing is we are taking the images, then at some point within the notebook, which I will show, we will randomly add noise to it. So and that will be the input data, and the output will be the uncorrupted data. So the idea is we are feeding a corrupted data into the model, and we are training it to learn to generate a clean image, a denoised image, which is where the name comes from, the denoising autoencoder. So we have the network architecture. So this is where we add the noise, and this is just randomly adding noise to the images. We can train the model. This should, sorry. Okay, this should not take more than a couple of minutes. So just make sure that the GPU is connected. It is. Just bear with me. Well, while we wait for that, we can just discuss some more about autoencoders. So yeah, so the denoising is very similar to the other technique discussed during the presentation, which is the which is the image completion. So in this case, in the case of the image completion, a part of the image is removed, and then the model is trained to try to predict that. That is very similar to what we do here, where we add some noise to the image. So this is the same image with some noise added in. Let's go back to this. Okay, it's training. Should be done shortly. So now, as mentioned during the presentation, autoencoders are actually not limited to images. This is also used for audio as well. So where you can have an audio that isn't very clear, and you can train a model to take in a corrupted audio, which we corrupt ourselves, to then predict the clean version of that audio. So actually, I think this is pretty low already. I don't need. We don't need to wait, so we can stop this. I'll be sharing the link to the notebooks so you can run it and play with it as well. Please just make sure to make a copy of it so you don't edit the same one. Just make sure it's public. Okay, let's stop this. We can resume training if we need it. So that has been stopped. So now we make a prediction on the first 5 images in the test set. So this is an example of a noisy image. As you can see, this is the number 7, and some Gaussian noise has been added to it to make it noisy. And this is what the model predicts. So yeah, this is denoising. So we can run a few more as well. This is the noisy image, and this is the denoised image. Noisy image. Okay, that's exactly the same. Okay, so noisy image, noisy image, and denoised image. So yeah, so that's a demonstration of autoencoders for denoising. So now we can come to, so this is, we need to stop this. Okay, so this is an example of a notebook that converts black and white images to colored, adds color to black and white images.
Hi, Sig. There's actually a question on the stream.
Oh, sure.
So the question is, Barak asks, in the case of simple noisy MNIST digits, what was the training data fed in the learning phase? Was it noisy pictures with their clean version as the reference?
Exactly, yes. So the input to the image is the, I'll just get back here. So yeah, so this is where we add noise to the image, to all the images. Now the input to the image is the noisy image, the image with the noise added in, and the output is the original image without any noise. So this is our X and this is our Y. So by training this, we are training the model to try to predict the original image given the noisy image.
Yeah, cool.
Did that
Thanks
answer
for
your
that.
question?
I hope so. I mean, if there is follow-up question, we can get it.
Sure. Okay.
I'll leave. Yeah.
Sure. So yeah. So this notebook, for the most part, is taken from. There's the link. Someone posted this on GitHub. So the first thing I do is to clone the repository, so I have access to this person's models and data. Here we import the TensorFlow packages. See. Okay, so yeah, so this is something that I actually found very, very interesting when I saw this notebook, is that this person is loading, so rather than loading JPEG images, they are loading binary files, which is in NumPy. So this is something that I actually learned at the last project I worked on, which is that it's actually faster to load binary files than it is to load images like JPEG and whatever. And we were able to speed up the training time of the model by just converting all the images into binary files like this, which is possible using, I believe it's using, so if NumPy is imported as NP, then it works as numpy.save. So this way you can save an array. So an image that has already been loaded into an array, you can then save the array as a binary file. And and the loading of binary files happens much quicker than normal image files. So I believe I actually ran this. I don't really remember, but it was definitely over 10 times faster than loading JPEGs or whatever. So, okay, so we have the repository downloaded. The images as binary files. So printing the X has 190 images and the test set has 9 images. They are all, the dimension is 64 by 64 pixels as well. So now in this case, what we are doing in this case is, this is also a simple architecture. Now, the difference between this case and the previous one is here, the input is also a 64 by 64 pixel image, but with only one channel because it's grayscale, right? However, the output is 3 channels because what we're predicting now is a color image, which is in RGB. So let's run this. Okay, so in this case, the loss is using the mean squared error and also using an Adam optimizer with the learning rate set to be this. Okay, so now let's train the model. So just like the last time, we won't necessarily wait because this will even take longer than the previous one. So we won't wait for all 500 epochs. So we can let this run for about 200 epochs, and then we can try out and we can see the output. So, so yeah, while we wait for this, if there are any questions, I'll be happy to answer those. Okay, again, I'll be sharing the link to this one as well. So yeah, please follow along, make a copy of the notebook, run it as well. And okay, I think 200 epochs is definitely going to take a long time. We're just at 30. Okay, I think we can stop this and see how it performs. Okay, so this is the input image, black and white, and this is, oh boy, oh sorry, thought I changed that. So this is the output. Okay, so I mean, it's not perfect, but we see that it's getting there. So it gets better the longer we train, and also the more complex the network is. This is still a very simple model, just 3 convolutional layers here, and 3 in the encoder, and 3 convolutional layers in the decoder as well. It's also possible to increase the size of the latent representation. At the moment, it has we're giving it a depth of 256, but of course this can be increased. And yeah, that's it on converting black and white images to colored images. Any questions?
Hi, Sage. Yeah, thanks for the presentation. Yeah, that was quite
Yeah,
interesting.
yeah,
Yeah.
very fast, quick, but
Hmm.
straight to the point.
Yes. Yeah, I mean, yeah. Yeah, so we can take some questions. So there's one question from Dimitri. Uh, have you tried to classify the images with noise and without noise to see the difference?
Hmm. Sorry, I don't quite get that.
Mm, okay. Um, yeah, Dimitri, could you please clarify the question a bit so that we, Sage can help you out? Yeah, thanks, Pablo. He likes the presentation. Okay, while we wait for the question, yeah, maybe like I had a question. So
Sure.
I've seen like these blog posts or uh, pay services that allow you to colorize these images. Do you think they are using autoencoders or are they using something else?
I think they are most likely using autoencoders. So now they might also be using GANs, but the
Hmm.
network architecture would still be autoencoders. And the reason for that is so when you use autoencoders is usually when you're trying to get an output that is the same or similar to the input. So like if you look at um, normal um, projects to use artificial neural networks. So you're doing classification or regression. You're feeding an image and you're saying predict something. Is there a dog there, or predict the classes? So those situations don't require autoencoders because although the input is an image, the output is not an image. However, in this case, so like whenever you're dealing with uh, like like a situation where the input is like an image and then the output is also an image, or if it's an audio file and the output is also an audio file, then that would require the use of autoencoders. So yes, so in this case we have a situation where we are feeding in a noisy image and we're getting out a cleaned image. Both are images. We're feeding in a black and white image, and we are getting out a colored image. Like I mentioned in the previous project I worked on, where we are feeding in images, and we are getting like outputs or segmentations of where is weed or crop or something like that. So in those situations, the output is also kind of similar to what the input is. So yes, the short answer to your question is most likely they are using autoencoders.
Hmm. Okay. And so what would be like the training set for it? So because you need both like the colored and other version or grayscale version of the image, right? Or
Oh yeah, yeah. So the great thing about it is that the same inputs, the same image you're using as the training set, is
Mhm.
also what you are manipulating to create your input and your output. So in our
Okay.
case, we took the same image, we added some noise to it. So the noisy one became the input and the original became the output. Or in the case of where we are using, so the data sets used, I believe, for the image coloration is likely the celeb faces, where with the faces of celebrities. So all you just have to do is take the same image, convert it to grayscale. So now you have the grayscale being the input image, and then you have the colored image being the output, what is being predicted.
Okay. Yeah. That makes things clear. So I think we have a couple of questions on the chat. So
Sure.
Martin asked, can you maybe also talk a bit about how you would use autoencoders for audio data?
Oh yeah, yeah, absolutely. So yes, so it is used exactly for denoising, exactly as you would expect for denoising the image.
I think we
yeah.
lost
Yeah,
you a
sorry about
bit.
that.
Yeah.
Yeah. So just like in the case of images, you take your audio files, you add some noise into it. You use the noisy audio as the input and the clean audio as the output. And that way, just exactly as it is in the images, you can use it to denoise audio. You can also use it for reconstruction of audio. So in cases where the audio isn't just noisy, but parts of it are lost in transmission, then you can use autoencoders to sort of fill in fill in the blanks. So I mean, so if it's applicable to audio, then it's also applicable to any kind of radio signal. So even transmissions of Wi-Fi or anything at all. So yes, autoencoders they have a lot of applications.
Mhm. Okay. And would it also work in the same way, the training, that you manipulate the original audio signals and then train it?
I believe so. Yes. So I've never done any work on audio using autoencoders, but I have read a few papers that discuss
Mhm.
that. And yes, that is exactly as it was used. So what's actually interesting about that is, so like one of the ways that people deal with audio for machine learning is to actually first convert the audio into some sort of imagery. So I'm not quite sure. I believe it's called I think it's a spectrograph, or I'm really not sure. Sorry, I haven't really thought about it in a while. But so yeah, so to sort of so to run models on the audio, they first convert them into images. That way, you can use your convolutional neural networks and all the all the other techniques you would typically use on images. Then you run it on that. Then you convert it back to an audio after you've done your done your analysis.
Mhm. Okay. Yeah. So Martin says thanks. Yeah. And yeah, we have another question. So could you please, so Barak asks, could you please elaborate about the practical usage or advantage of the meaningful compressed state of the data? How is this property being used in practice? Where is it used solely for compression?
Oh yeah, absolutely. So yeah, so now I should say this. So I believe when autoencoders first started coming into style, like one of the very first applications that people thought of was to use it for compression, right? Like, oh, if I can compress, then I can use it as I would use my WinZip or my WinRAR, compress something and send it over. However, it is not really used in practice for that kind of compression. It is, however, used for compression within machine learning itself. So like last year I worked on some on time series, right? So as I mentioned before in there, so I participated in this hackathon, and we were getting this wind energy data. So now we were also applying a lot of feature generation, a lot of feature engineering. So after applying all the feature engineering, we would end up with 200, 300 features. And that made which made it very difficult to train a model, because even like the number of observations we had were going to like 300, 400,000 entries. So yeah, so if you're having 300, 400,000 observations and you're having 300, 400 features, that would take the model a long time to run. So now, typically in normal data science, what you do is you apply PCA, right? Principal component analysis. However, autoencoders can do that as well. So that's what we did. So in this case, I believe I will share my screen again just to drive home the point.
Yeah, go ahead.
So using this, so the idea was coder, we fed in the 300, 400 features and got this latent representation, reconstructed the image. So now, I'm not sure if I mentioned this during the presentation, but now, like, you might ask yourself, like, what is the use of putting in an input and generating the exact same input as well? Well, the reason is that when you do that, that is telling you that what you have here in the middle, that it's meaningful enough, um, to reconstruct the original input. So this tells you that this small part that you have here is useful enough and it's meaningful because you're able to reconstruct the input from this. So now, once that is done, you can throw away the decoder, this half part, and keep this part. So what we did then was we kept this part, we kept all of this, and then we connected. So the normal machine learning model that we wanted to use to predict the time series, we then connected that to this part. So now you can feed in the original image. It makes inference and outputs this small part, and it's this small part that is actually going into the machine learning model, and that way we were able to like run the model faster.
Yeah, that
So yeah,
explains.
so that's with regards to like outside of computer vision, but within computer vision, yes, it has lots of applications. Like um, as I mentioned, I worked very recently on a project with where we um, where we built a model that would take in an image or a video and would output whether there's like weeds or whatever. And in those cases, those were input images and output images as well. So the inputs were images and the output were images. And we used autoencoders every step of the way.
Yeah. Yeah. I believe you have an article for this, right?
Yeah, I sent the link.
Okay. Is it already published?
This one is published, yes.
Okay. So if you want, you can actually share your screen, and I can also share this. Uh,
Oh yeah.
yeah, so that people get a bit more idea about this. Yeah. So Barak, thanks you for the interesting and practical talk here. Okay.
Sure.
So yeah, let me just add you.
I am sharing, right?
Yes.
Oh yes, cool. So yeah, so this is an example of it in action. So I don't actually have the. So yeah, this particular article is mostly about this. So it doesn't have the images but yes, but this is an autoencoder network as well. So what we did was, so this is a bit more complex than what we discussed, but in this case, we are using a ResNet 50 model as the encoder, and then we use this is the ResNet 50. So yeah, so this is the ResNet 50 architecture. This was used as the encoder, and this was used as the decoder. It's called a pyramid pooling module from a model called PSPNet. This was used as the decoder, and the goal then was to sort of detect weeds in an image.
Cool. Thanks. So there's
Sure.
another question. Uh, so is this autoencoder to detect anomalies about the time series I meant that you mentioned?
Oh yeah, sure. So no, it wasn't to detect anomalies, and yes, anomaly detection is another application of autoencoders, which I believe I didn't mention. But no, but in the case of the time series, it wasn't used for anomaly detection. It was used for dimensionality reduction.
Hope that answers your question. So I had another question. So like, let's say if someone new wants to get into or wants to try out some thing in autoencoders, so what would you recommend for them?
So I mean, first things first, I'll recommend the two notebooks we just went through. They
Mhm.
Yeah. So now autoencoders by themselves are really simple. That's one of the best things about it. It is a relatively simple concept, but you can do a lot with it. So yes, I would recommend. There is also a Keras. So this denoising with the handwritten digits was taken from Keras's website. So they also have a bit on that. But yes, but I would say that with autoencoders in general, because it has so many applications. So like there is also a type of autoencoder called a variational autoencoder, which we actually didn't get into. So now a variational autoencoder is a bit different in that it's mostly used to generate images. So very recently, some people published a paper where they were able to use a variational autoencoder to generate images that looked just as realistic and quite competitive to GANs. So now GANs are not the only they're not the only generators in the market. Now you have variational autoencoders. But yes, so yeah, they are relatively simple concepts. You just have to remember that an original autoencoder is about feeding in an input and generating an output that is identical to that same input. And then you can start to play around with it to get variations, for whatever it is that you're hoping to solve.
Mm-hmm. Yeah, sounds really interesting. Like, yeah, I would be interested in like learning more about this variational autoencoder and how they compare against GANs. Yeah, I should check this out. Right, really interesting. Yeah.
Yeah. So they performed better. So they were used to generate faces. And I actually wished I had opened that up before. So it was, I believe it was published by NVIDIA, if I'm not mistaken. It was one of those NVIDIA publications. So for a long time, like everyone really thought GANs were that you need a GAN to generate something of that quality, but not anymore.
Yeah. Yeah. Quite cool. Yeah. I think there are no more questions. So Dimitri says thanks. Yeah, I think so. We are slowly coming to the close of the official part of the meetup. And so I would really like to thank Sig for all the time that he spent and like all the cool examples that he shared. And yeah, I'll also put a link to all the presentation and the notebooks in the meetup page so that you can find them later on. And so now you can actually join us for the networking call. So it's like just a small Skype call. So you can just join and like ask any questions related to the meetup, or even give us feedback or what topics you would like to see in the future. So I'll share the link to the meeting right now on the uh, on the YouTube comments so that you can join us. Yeah, I guess, yeah, Lucas also says thanks. Thank you for joining us. Yeah. And Pablo, yeah. Yeah. So I hope to see you all in this call like pretty soon. So yeah. So yeah, we'll see you in the call, right, Sij?
Yeah, definitely.
Yeah.
I'll need the link as well, though. I've been trying to
Yes.
copy it off my screen, but
Yeah, I'll share it.
apparently you can't copy something off your screen. Someone needs to create that feature.
Yes. So yeah. Then I'll see you in the call then. Thanks a
See
lot
you
for the
soon. All right,
presentation. Then
cool.
yes, thank you everyone for joining, and see you hopefully in the call. Then have a good evening and see you. Bye.